think we'll get started here. It's a pleasure to have Dan.
Who are you?
Slichter, Dan is, of course, no stranger from not for the NIST. Dan did his undergrad at Harvard before moving on to Berkeley, where he was a first fellow at qubits. He got many awards there. He was a first fellow, got the first thesis prize. At that time, he decided to leave the dark side and start moving back to qubits, and he almost made it like all the way to the light side, but instead works on ions. So he has been working at NIST for some time now. He was an NRC fellow and then a Kaufman fellowship. And then they wisely decided to keep him there. Dan has done a number of groundbreaking experiments, has several projects. Maybe among many different things, most notably, more recently, they've been working on these experiments where they've shown the highest fidelity qubit gates across the board for a platform. I think it's the only experiment where a group, rather, where I would read a paper and see an error bar that's consistent with one and actually believe it as far as the fidelity. So I'm sure we'll hear about that today. Thank you for being here.
Yep. Thanks, Adam, for the introduction, and thanks everyone for coming. Is there a way we can get the lights down a little lower on this? That would be helpful. I'm not a dark background slide person, but it will. Yeah, there we go. So thanks for the invitation. Thanks for the opportunity to come talk. I'm the Colloquium speaker, but this is work that's been done by many, many people. And in fact, there's a number of people who've done important work that's contributed to everything in this talk whose names aren't even up here. I will call out one person in particular, which is Didi Leibfried, who is my sort of partner in crime and running a lot of the quantum information processing show over here. But there are many, many people who I would like to thank for their hard work in the science that I'm going to talk about today. I figured I'd start just by telling a little bit about the NIST ion storage group. Why is it even called ion storage? Well, in the old days when beam clocks were the best clocks that you could get, Dave Wineland came to NIST and started this group. And the idea is, well, maybe if you could hold on to the atoms instead of just having them fly by, then you could interrogate them for longer and you could get a better clock signal. So let's store some ions. So that's ion storage group anyway. So that's why the funny name. Anyway, the group was started many years ago by Dave and various other folks, including Jilla alum Jim Bergquist. We trap ions with a combination of Paul traps based on electric fields that oscillate and Penning traps based on static magnetic fields. And we do a lot of stuff. And I'm going to talk to you about a little corner of this stuff today in terms of quantum computing, but we also have work on quantum networks. We also do things where we study quantum fundamentals and quantum optics, measurement, squeezing, things like that. We have the world's best systematic uncertainty for clock accuracy at 9.4 times 10 to the minus 19 fractional frequency uncertainty. We do have world records in molecular ion spectroscopy with comb spectroscopy. We're using ions as quantum-enhanced sensors and to probe surface science phenomena. And we're simulating many-body physics and simulating tunable spin Hamiltonians and bosonic Hamiltonians. There's many, many things going on in the group. And there are many staff scientists beyond myself who are doing this. And so this is sort of a somewhat recent picture of all of our group. And so all these people are working on lots of these different projects. I encourage you, if you're interested in any of those sorts of things, to check out the group website at this QR code here. Or also, if you're interested in potentially working on some of these things, to get in touch with me. So anyway, I just want to point out that what I'm doing today is just a small fraction of what I'm talking about today is just a small fraction of what our group does. So let's get started. I'm going to talk a little bit about quantum computing. And so since I'm not sure how everybody fits in, let's start off really easy. Let's talk about classical, by which I mean non-quantum computing. And this uses bits to encode information. A bit is just a system with two possible states. It's on or it's off. And I think we all know you encode digital information as strings of bits. And that string of bits could be an image. It could be an email. It could be a piece of a PowerPoint talk. It could be some of your data from the lab, right? And there's lots of different physical forms in which we have bits. We use bits in transistor voltages. We use bits that, although less these days, are tiny magnetic domains that might point one way or another. All of us use a lot of these kinds of bits that are actually pulses of light in fiber, and the encoding is a lot fancier than on and off. And similarly, a lot of us use all of these bits. We use billions and trillions of these sorts of bits on a regular basis, right? Has anybody ever asked you which is the best bit? Which bit should we all be using, right? I mean, they all have different advantages. They all have different disadvantages. They all have things they're really good at and things that they're less good at. So then what's a qubit? A qubit is a quantum system with two possible states, right? And the canonical thing would be a spin-a-half particle in a magnetic field. But you could also use, two states out of the many states in an atom. You could also use states in a superconducting circuit, as I did for my PhD. Or you could use states of a light field, photons. They could be optical photons. They could be microwave photons. They could be whatever you want. But the point is, there's many ways that we can realize qubits as well as classical bits. And the idea that there's one right one, or that one of them is somehow better than the other one, it's like, well, it depends on what you're trying to do with it. Right? So anyway, so what I'm going to talk about today are trapped ion qubits, but this is I just want to point out for all those of you who are like, well, are ions really the best? The question is, at what? So what makes qubits different from classical bits? There's sort of three things that I'll point out. The first thing is you can have superposition. So if you have n bits, you can put them in some configuration, but it's only in that one configuration. If you have n qubits, there are 2 to the n possible configurations you can be in, and you can be in more than one at the same time. So for example, if you've got 2 qubits, you have these 4 possible states they can be in, and you can actually be in a superposition of all of them at the same time. So the ability to be in this sort of large superposition, one way of thinking about this is you have an exponentially large state space, an exponentially large Hilbert space in which you're operating with these qubits. The second thing is entanglement. You can actually make states of qubits where you can't actually separate this state here, for example, as well as a state of qubit 1 times a state of qubit 2. The states are somehow intrinsically linked. If you were to take that state and measure it, and you measure the left-hand qubit as 0, the right-hand qubit will always measure 0. If you measure the left-hand qubit as 1, the right-hand qubit will always measure 1. But if you just look at the measurement results of a state like that in isolation, you re-prepare it and remeasure it, it just looks random. So it's kind of a thing where, and there are many analogies that people have used, but basically, unless you can see the entirety of the entangled system, it might just look like noise. But then once you can see the whole thing, there's correlations. And this is sort of an essential feature for qubits and what makes them powerful and useful. And then finally, these quantum states here, implicitly we've drawn, there are these normalizations here, but these can have different amplitudes. And the different amplitudes can actually add and subtract. They can interfere constructively and destructively with each other. And they can maintain their sort of quantum amplitude over time. And this is another sort of key feature of qubits. All right, my battery has just died, so I'll fall back on this. All right, so let's talk about classical computing so that we have a little analogy that we can make for quantum computing. So if you look on the motherboard of some processor, it'll look something like this, and you'll see some gray boxes that have some little wires coming in and out of them. And so this is basically a cartoon of that. So you've got a gray box, and you've got a bunch of wires that are coming in and out. There might be sort of order the same number, but they don't have to be the same number. And then inside that box, there's a whole bunch of sort of logical operations that can get performed. You can use ands or ors or nots or other things like this, different combinations. But you can basically choose any algorithm that you want to perform on these classical bits and implement it out of these sort of fundamental logic gates inside. It makes it sort of a universal set. And then in principle, if you want to know if you have this and it's a mystery what's inside, you can say, well, I'm going to figure it out. But in general, you would have to run all the possible inputs and see all the possible outputs in order to get that. So you'd have to run it 2 to the n times. What does a quantum computer look like? Well, a quantum computer is another sort of box like this. You'll have n qubits that you send in, and we need these qubits to be quantum coherent in the way that they'll maintain their amplitudes, the phase and amplitude of their superposition states, as I described. And then inside, you've got a universal quantum gate set. And these quantum gates are called things that are not and or nor, but they're called things like CNOT or Hadamard or T-gate, or things like that. And they're just names. And basically what's happening is you piece these together in the same way that you'd piece together ands or ors or nots. And with that, you'll basically create superposition, create entanglement, cause interference between the amplitudes of all these different qubits that are running through the processor here. And then this will produce the algorithm that you want to do. So what does it actually mean to be doing these gates? Well, so the way that people usually decompose quantum gates is in two different forms. One is sort of single qubit gates, where you're controlling the state of just one qubit at a time. And very roughly speaking, this sort of helps you make superpositions, although that's very rough. Multi-qubit gates that maybe are 2 qubits at a time very roughly can be used to create entanglement. And it's a charger, it's a USB charger thing. I appreciate it. I'll just gesticulate. What about this? Yeah, this looks like it. A pointer does the main thing that I need. So multi-qubit gates, roughly speaking, are used to create entanglement. And then basically a quantum algorithm is creating and manipulating superpositions and entanglements in many qubits at once in sort of a very carefully orchestrated way, such that the amplitudes interfere with each other in a very nice way to produce some desired quantum state that you want to do. What does this actually look like? You perform gates by applying some kind of control signal, usually a pulsed control signal, to the qubits. And so here's a picture from paper from back when Jerry Chow was a small shot. So you have some kind of waveform, some pulses, and you can see they're precise timings, they're precise durations, precise frequencies, all these things that have to go into these pulses. And these pulses might be from lasers, they might be microwave pulses of magnetic fields, you might be electric field pulses, but there's some kind of something like this. And you need to, in order to perform this quantum computation, have these pulses be able to reach in and touch all of the qubits in your processor and be able to do so in a way that you can control them individually. So that's a hard, challenging problem. So this is one of the big distinctions with classical computing. So a quantum circuit is what we call sort of a quantum algorithm. This is example one off the IBM Quantum website. And basically, the circuit diagram looks like this. Each line across represents a qubit moving forward in time. And then each one of these sort of colored boxes represents an operation, a gate, that's being done involving those qubits. And so you have 2 qubit gates that you can see that will connect to qubits here. And you have single qubit gates that are drawn just as these squares that just do something to a single qubit. And so basically, a quantum algorithm will look like something like this, some symphony of 2 qubit gates and single qubit gates, and there are other kinds that you could think to use. And this will produce the desired result if you get them all right. So now we've got this quantum computer, and you'd say, all right, we've got superposition. So if you want to just test all the 2 to the n possible inputs at once, just put in a superposition state and run it through, and you'll compute everything in parallel. And this is what everybody would like to say. But it doesn't work that way. And the reason is, at the end of the day, you have to measure your qubits. And when you measure quantum systems, they collapse. And what you get is n classical bits out. And so even if you have this sort of exponentially large state space inside your quantum computer, in here you have a state space that's 2 to the n big. And out here you'll get n bits of information out about that state space. So that's a really big down select. And so basically, and furthermore, those n bits are chosen randomly by the measurement process. So you need to have a really smart algorithm that figures out how do you exploit quantum interference, basically, of the different amplitudes in here in order to get some answer that you care about with a reasonable probability. So this is sort of the key feature for quantum computing. The second part is that everything that's going on here is really sensitive to any sort of noise or imperfections that you might have. And so that means that all of these operations, all these things that go on in here, and the coherence of the qubits themselves, and your ability to measure accurately and sort of faithfully output a bit that reflects what the qubit state actually was, those need to be as good as you can possibly make them. And there are ways that I won't even go into today. It's this whole other field of quantum error correction where you can think about saying, well, they don't have to be absolutely perfect, but if they're above a certain level of performance, then we can sort of concatenate them and trade various other things in order to make an effective qubit that's more perfect. I won't talk about that today, but I'm happy to answer questions about that. And there are people in the audience who are much more expert than I am as well. So, having given a little background about quantum computing, I haven't talked about ions yet within that. So all of that is generic to whatever kind of quantum platform you want to use. I'm going to talk about how you might do this with trapped ions, which is one particular platform that has certain advantages and I think is compelling for quantum computing. So first I'll tell you a little bit about trapped ions. I'll tell you about how people are thinking about scaling up trapped ion quantum processors. And then I'll tell you about some features of basically doing the control, like the gates, as well as the readout, the measurement, using features that we've actually integrated into the ion traps themselves, and why that is useful for scaling. And then finally, at the end, I'll sort of just remind of our little cartoon vision of where we're going from here and what we're doing on that path. So let's get started. So trapped ions are, a really nice feature for a really nice platform for quantum information processing. So if you want to make a qubit out of a trapped ion, you can sort of pick two internal energy levels. And we use atomic ions. We trap them in ultra-high vacuum. They're very isolated. They can be very coherent. This is nice. Something that not everybody always thinks about is that the motion of a trapped and laser-cooled atomic ion inside this trap is also a good quantum degree of freedom. It's a quantum harmonic oscillator. And so you can say, well, why would you use a trapped ion? Well, the qubits, every time you load one of a certain species, it's identical to the last one and all the future ones that you'll load. So that's a nice feature. You can hold on to them for hours or days or weeks even. So in deep traps, particularly in cryogenic vacuum, which we use for a lot of our things, you basically lose ions via human error. And there are some people in this room who have named their ions because the ions stick around in the trap so long. So this is a nice feature. The coherence times can be very long. People are have seen things with dynamical decoupling approaching an hour. You can do the control that I was talking about, these gates, with very high fidelity. This is sort of, the state of the art for, there are other technologies that are also very good, but this is sort of the state of the art for gate fidelities. You can do the measurement with very high fidelity. And then also importantly, for running a quantum algorithm, you can change up which qubits can talk to which other qubits on the fly. So if you have a set of qubits in a processor that are designed where you lay them out lithographically, and then you need a qubit here to talk to a qubit there, you can't move them together. They probably don't have a direct interaction, and so you have to do something where you do swapping of information through a bunch of neighbors in order to get there. But with ions, you can actually physically move them around and change the connectivity. But basically, just from a quantum science standpoint, these are very coherent. They're very tunable. You can couple them in different ways. You've got spins. You've got quantum harmonic oscillators. What a great playground. So how do we hold on to ions? We use, for quantum information, RF ion traps, and we use what we call linear RF ion traps. So basically, this is the canonical design. You take 4 metal or conducting rods of some sort, and you put an RF potential on those rods. And if you look on the end here, that makes sort of a quadrupole right here. And the ion wants to sit in that quadrupole. Well, a quadrupole is not a minimum, right? It's a saddle point. But what we do is, because it's oscillating, we flap the saddle up and down. And if you flap the saddle up and down at an appropriate rate, given the charge and the mass of the ion and things like that, by the time it starts to roll down the downhill, it will have turned into an uphill, sort of effectively. And so on a time average sense, the ion feels a confinement and doesn't want to leave, even though it's not actually truly a minimum if you just look in freeze frame at any given moment in time. But this is why it needs to be oscillating at RF instead instead of just a DC. If it was a DC saddle, the ion wouldn't stay. And then in the third dimension here, we can use DC potentials to make sort of a well like this to hold the ions. And if you put a couple of ions in there, they're charged and they will repel each other. And so depending on the shape of the confining potential, here it's sort of weak along this axis and tighter radially, they may sort of line up in a little string if you set them up like that. Now, this is something that people historically made in a machine shop, or maybe laser cut something. But something you can do is to kind of take these electrodes and envision unfolding them onto a plane. And if you unfold them onto a plane like this, you still have this quadrupole. The symmetry is lower, but you still have this quadrupole and you can still trap. But now if you want to make some complicated electrode structure in order to do the trapping, you can make this in a clean room. You can microfabricate it using the kinds of tools that we use to make computer chips. And so this enables you to make very complicated electrode structures that you might use to make very large-scale traps. So this is sort of a compelling thing. I recognize that there's a lot of people from the neutral atom community here, or as I like to call them, the uncharged ions. And so I want to just contrast a little bit for people differences between a real trap and an optical trap. So the trap depths that we're talking about here for RF traps are between 100 and 10,000 Kelvin. That's not a typo, it's Kelvin. So you can trap directly from a thermal beam from an oven. So trap depths are much, much larger. You'll keep the ions for much, much longer. This is, I'm teasing you a little bit there, obviously, as I've said, reasons why you would pick one over the other. But this is a major difference that you should be aware of. Another thing that's really important to note is that the confining potential doesn't depend on the atomic state. So you don't, with an optical trap, you have to take care of what states you're going to be in. You may have untrapped states, anti-trapped states, and you may want to choose things like magic wavelengths so that the trap doesn't shift your transition frequencies or your confinement. Here we can basically, unless you're running a really, really high precision clock, you can basically neglect shifts due to the trap, and the confining potential is basically independent of the atomic state. So it's a different regime to be working in that you should be aware of. So hyperfine qubits are what we generally use in our group. We use basically two levels in the ground state that are sort of separated by some kind of microwave frequency. The dephasing times are seconds to minutes if you have a clock state, and the decay time, the T1 here, is basically infinite for all intents and purposes. This is similar to if you had an uncharged ion. And then you've got some excited level that's kind of a petahertz up. And you do laser cooling and optical pumping using 1 or 2 resonant lasers that are sort of microwatt levels of power. And with this, you can actually cool down to the ground state of motion effectively, or close to. And then if you want to do qubit state control, you can either use a stimulated Raman transition with a couple of lasers that have a beat note at your qubit frequency but are detuned from this level. And typically for high fidelity gates, those have relatively high powers, sort of watt level. You can also use microwave magnetic fields or gradients, or static or radio frequency magnetic fields or gradients to perform gate operations. And then for the readout, you turn on resonant lasers and you have state-dependent fluorescence. So similar to how some other experiments do, if you're in one state, you'll be resonant and you'll scatter and reabsorb and scatter and reabsorb. If you're in the other state, you won't do anything. And so if you look on a camera, you'll see the ion is either fluorescing, giving off light, or not fluorescing, and that tells you what the state the ion was in. So this is how we do the readout. The spin and the motion of ions are basically the quantum degrees of freedom of relevance here. And we can basically cool the motion until you're in the ground state. And then we can perform transitions where we either flip the spin without changing the motional state, or we flip the spin while also changing the motional state. And those of you who speak Hamiltonian will sort of look at those and be like, ooh, I think I recognize these things from like an atom coupled to a cavity. It's exactly the same physics as that, but here we have a harmonic oscillator that's the motion instead of a cavity. So using these sidebands that I described, you can make Jaynes-Cummings or anti-Jaynes-Cummings interactions. You can sideband cool to the ground state, and you can put on state-dependent forces. So why do you care about state-dependent forces? Well, if you have ions, if you have several ions and you trap them, they're going to repel each other. So here is a picture of 4 ions that are kind of a few microns apart from each other in a trap. The direct spin-spin coupling between the ions is millihertz. It's basically negligible. So there's nothing like that. There's no exchange interaction because there's no overlap of the wave functions. So we have these really nice qubits, but how are we going to get them to actually entangle with each other, right? This sort of seems impossible because they're just never going to get near each other enough to use these tools. So basically what we do is we turn a bug into a feature. We say, well, they repel each other. Well, that just means their motion is very strongly coupled, everyone, right? So then you say, all right, now we actually have to think about the motion of these ions in terms of eigenmodes that involve all of the ions together. They're so strongly coupled that, for example, if you have 2 ions, they'll either do this together or this together. And those are the 2 eigenmodes of motion. And in general, you'll have 3n modes. And if you look at this, you'll see all of these motional modes here involve the different ions. And so if you were to able to encode the quantum information into this motion as a quantum bus, you could use it to couple the ions. So if you think about those Jaynes-Cummings types Hamiltonians I just showed you, you'd think about, OK, what about a cavity-mediated interaction between 2 atoms? This is the same kind of a thing. This is a harmonic oscillator-mediated interaction between 2 spins or more than 2 spins. It's just that the harmonic oscillator we use is a shared motional mode that the atoms are coupled to, as opposed to a shared cavity mode that the atoms are coupled to. In order to do this, we need this spin-motion coupling. We need to be able to apply these sort of sidebands. So that means we need state-dependent forces. And in reality, basically, within a trap, anything that you see out there where ions are coupled together, it's all mediated by the motion, shared motion of the ions. There are 2 caveats to this. One is that there are some heroic folks who are working on Rydberg ions and doing ion-ion coupling that way. Another is that you can actually entangle ions with photons and then perform a Bell state measurement on indistinguishable photons to create remote heralded entanglement between ions. And people make large ion crystals talking with these things. So here's something from Innsbruck, and here's something from IonQ, and here's something from our group. And you can make, nice, large, pretty pictures with lots of ions in them. But at the end of the day, if you want to do a large-scale quantum computing type activity, you can't get enough individually controllable ions like this into just one potential well. All the things fall over for reasons that I won't describe. So how are we going to scale up a trapped ion quantum processor? Well, fortunately, Dave Wineland and pals in our group pitched this, basically a year after they did the first entangling 8. They're like, here's how we're going to scale. And it's still, in my opinion, the best idea. So the idea is you make a little ion city, right? And the ions, you can move them around, right? And so you basically have different zones in your ion city. And some are the places where you have memory, and some are places where you do gates, and some are places where you do readout. And we call this the quantum CCD architecture. And so all of these little gold things here are meant to be trap electrodes. Didi made this figure about 20 years ago. It's still good. But so by applying different voltages to these trap electrodes, you can move the ions around. You can take the ions that are parked on 73rd and take them uptown to 77th to do readout, OK? And so then the idea is you don't have to go to huge ion crystals. You can have a bunch of small ion crystals in a bunch of different locations. It makes the motional mode simple. It makes the addressing simpler. You don't have to focus down in a tiny crystal and things like that. And then you can move the ions around to reconfigure which ions talk to which ions. And by doing that, you can reduce the number of gates versus having to swap through things. You can think the fidelity might be pretty high. And so now you just need control beam access, lasers and microwaves to these zones. And then this is something you can microfabricate. Right? You could envision making something like this in a clean room, and now, voila, here's your scaled ion trap. So I want to point out that you can also scale with this other scheme here, and we have work on this for quantum networking, but I won't talk about it today. But once you start doing something like this, where you're moving ions around all over the place and doing long algorithms, then you start to run into the need for 2 ion species. And the reason you need 2 ion species has to do with cooling. So let's say you've got 2 data qubits here, right? And eventually, over time, either your ion transport was imperfect and left a little motional excitation in the ions, or there was electric field noise in the trap. The motion is not near the ground state. And because you're using the motion as the coherent quantum bus for all of your entangling operations, this hits you in terms of your gate errors. So now you just laser cool, right? Just laser cool them back again. But the problem is laser cooling something that's holding quantum information destroys the quantum information. It's a reset operation. And so you can't just laser cool these qubits to get them cold again. So what are you going to do? The thing you can do is to add another species of ion, a helper ion, in with your data ions. And the helper ion has laser wavelengths that are not resonant with the data ion wavelengths. And so now when things start to get warm, they all get warm together because they're all coupled in the trap. Now you laser cool the helper ion. It doesn't matter if you reset the helper ion. It's not holding any of your important information. But the data ions, their motion gets cold without impacting their internal state, without impacting the quantum information that they're holding. So this is going to be really important if you're trying to run long algorithms, if you're trying to transport ions around. So this is a nice cartoon picture. And I also want to point out there are ways that you can do helper and data ions with a single species by using metastable states for shelving, which has been done by Innsbruck for many years, and other people are working on this more now. But we prefer using 2 different ion species for various applications. So one of the things that I kind of glossed over in this thing that I just mentioned is what do the motional modes actually look like for mixed species? Well, here we go. Let's say you have a mixed species crystal. You got your data and your helper. And these are basically the eigenvectors of the 2 motional modes. So one motional mode, they're kind of moving together, but they're not exactly equal. And one of them, they're sort of moving out of phase, but they're, again, not exactly equal. But they're sort of reasonably good. But now what happens in the transverse or the radial direction? Well, if these 2 species have somewhat distinct charge to mass ratios, as is the case for typical ions we use, then these modes tend to decouple. And so now you get one mode that's basically all this one moving, and one that's basically all this one moving, or very little of the other one. So then if you look at this mode here becomes very hard for the helper ion to cool, because it doesn't participate in it much. Right? And so that's challenging. It gets even more fun if you have a 3-ion crystal and you put your helper in the middle, because now you have a mode in the middle, this stretch mode, where by symmetry that ion doesn't participate at all. Right? So you cannot cool that mode by laser cooling this ion here. So what you end up with is, even in these sort of small crystals, there are some modes that are hard or impossible to cool sympathetically. And so that's going to limit your gate fidelity, your algorithm duration, all these things like that. So what we've done is actually a project where, led by Panyu Ho and Jenny Wu, where we can actually couple the modes in mixed species crystals. So this is a very busy picture here, but what it's showing is an ion trap, and there's a bunch of electrodes here. And what we're doing is we're putting oscillating voltages on all 12 of these electrodes. And these oscillating voltages are designed in a specific way, their frequency and their phase and their amplitudes, such that we're actually modulating the confining potential of the ions. And we're modulating the confining potential of the ions in such a way that you actually couple the modes together. You can choose several different modes, 2 modes, and actually couple them. And this lets you exchange motion between these modes, and this lets you indirectly cool. So let me tell you a little bit about how this works. So here I'm going to sort of show, here are 2 harmonic oscillators, right? Here's a mode that is weakly cooled, and here's a mode that's strongly cooled, and they start in some thermal state, so they have some occupations, right? And then when you come along and you laser cool the strongly cooled mode using your helper ion. So now that mode is cold. The weakly cooled mode didn't really get cooled. But now you perform this mode coupling, and you can actually just swap the occupations of these 2 modes. So now you swap such that now the weakly cooled mode is cold. It's in its ground state. And now you have the former thermal excitation of the weakly cooled mode now in the strongly cooled mode. And then if you cool again, now both modes are cold. And so you never directly cooled the weakly cooled mode, but you basically swapped it in to the strongly cooled mode, and you can sort of cycle through multiple modes in this way and basically, pull the excitations out of all of these modes in turn and leave them in their ground states, even if they can't be directly laser cooled. So here's some data from this. And so this is this in-phase mode, the stretch mode, and the alternating mode. And you can see that the stretch mode, this pink one, which I described as impossible to cool, we're reaching an n-bar of 0.02, so average phonon occupation of 0.02. So this is really good performance for a mode that you, by rights, should not be able to cool at all. So, so this is a nice result that you can get. I want to make an aside, which is that this mode coupling is quantum coherent. So again, for those who enjoy Hamiltonian, I present one. This is a beam splitter, and so you've got two modes, A and B, and you can couple them back and forth. And there's a controllable phase and a controllable strength G. And so you can do things like this. And what I'm showing here is, let's prepare the A mode with one phonon and the S mode with 0 phonons, and turn this interaction on and sweep the frequency. And you can see that basically, when you're on resonance, you can get the modes to exchange, right? Or let's basically sweep the time, and you can see, all right, they swap back and forth in time between the two modes. You can perform a beam splitter, you can perform a swap, you can perform a double swap, it gives you a phase. So there's all sorts of kind of fun quantum optics things that you can do. It's totally tunable, right? A nice quantum optics thing you can do is say, I'm going to put one phonon in each mode, and then turn on a beam splitter type interaction. And what you see is the populations of one ion in this mode and one ion in that mode, that's the pink, that goes to 0. And then here at that same time, you have the population of 0 in this mode and 2 in that one versus 2 in this mode and 0 in that one. So this is basically Hong-O-Mandel interference. Like the two phonons, they're bosons, they want to go the same side of the beam splitter. They don't want to go opposite sides of the beam splitter. This is kind of cool because we're actually taking two phonons that are at different frequencies and making them Hong-O-Mandel interfere, because the modulation of the trap supplies the necessary energy difference to make them sort of indistinguishable for quantum purposes. But so we can also squeeze the motion by modulating the trap potential. The impossible to cool mode becomes the protected during fluorescence readout mode, which is a nice feature. So basically, you can use ion motion as a platform for continuous variable quantum computing. I'm not going to talk more about this, but that's a nice thing. So the quantum CCD architecture, that cartoon, here are various sort of implementations of it that actually exist in the world that have been done by our group and other groups. Here is one that Quantinuum is now a company that's entirely predicated. Their whole game plan is do this quantum CCD thing. And their latest, greatest trap here looks like this. But the point you can see is all the laser beams here are coming in skimming the surface. They all come in from the side. And you can imagine if you have your city of ions and all the laser beams are coming in from the side, at some point that starts to fall over, right? So we got to figure out what to do next. We want to try and integrate the control and the readout as much as we can into the trap. So right now, all those nice quantum CCD traps, they live inside something, and then there's all these sort of grad student postdoc constructed optics and imaging things around it and stuff like that. And you do great science with that, but if you want to make a giant quantum computer, you got to think of something else. So we're trying to think about that. So the more we can integrate into the trap itself for control, it will be more stable, self-aligning, compact, and hopefully give us high fidelities and then be scalable. So the kind of the cartoon picture that we're pitching is a unit cell that looks something like this. You've got your mixed species. You've got something here to count fluorescence. I'll talk about that. You've got electrodes here for control. I'll talk about that. And you've got laser beams that come out of the trap, and I'll talk about that. So all of these things will be in the next feature. But eventually, the point is there's no external components to align. You don't need optical access. You just plug fibers and wires into your trap chip, and that's what you need. So let's talk about control. So integrated photonics for ion traps is sort of a new and very exciting technology, and I think everybody agrees an essential one if you want to scale up. So the idea is that you can make waveguides on a chip. It's like optical fibers, but that you can microfabricate on a chip, and those guide the light around the chip. So we think this is going to be necessary if you want to address optically at scale, because you can't come in from the side like with a neutral atom array. You can have a 2D array because the light goes out the other side, but not with an ion trap where you've got a giant trap underneath that blocks it. So currently people use passive components to basically send laser beams up. So here's pictures of waveguides routed around underneath, and then here's laser beams actually shooting up out of the trap, and they'll hit an ion, and you can perform cooling and gate operations and readout and things like that with them. So what are the sort of the challenges for this, which is sort of a new kind of technique? Well, the wavelengths are pretty short. They're in the visible or the ultraviolet, which is not where people have done most integrated photonics stuff before. There's materials challenges. Modulators are sort of not really a thing yet, and they will be probably too big for a while still, too. And so can we work without modulators? And then we also have to worry about noise and things associated with this. But so for scaling, what we want to do is we want to figure out, let's do things with low power laser beams, and let's do something where we can send one beam in, and it gets split to all the zones and just sent to all the zones without having to switch things on and off, without having to modulate the frequencies or something like that. Just global illumination, but delivered locally. So how are you going to do addressing like that? So one way you can do this, and this is work from Nathan Lisney and Justin Niedermeyer in our group, is to use micromotion. So what is micromotion? So you've got an ion, right? We've trapped it here in this trap. And what I'm showing here are the field lines of the RF electric field that it's used to confine it. And if you have the ion just sitting right here in the middle, there's actually no electric field there. There's no RF electric field there exactly at the center, so the ion sits still. And if you send a laser beam through that I'm trying to draw with this blue thing here with that K vector, and you look at the frequency spectrum of the laser as the ion sees it, it looks like this. It's a nice, sharp line right at the frequency that you want it. But now what happens if you use a small electric field that you apply on a trap electrode and you move the ion away from the null? Now the ion is driven, its motion is driven at the RF frequency by the RF electric field that is there. And so now the spectrum acquires sidebands. You're phase modulating the light in the viewpoint of the ion. So now you've got sidebands at multiples of the RF frequency. And in fact, if you go to just the right place, you can make the carrier disappear, and you have only sidebands. So now all the laser light is detuned in this ion's perspective by at least an RF frequency. And so using this, you can basically make very small position adjustments with a local electrode or a few, and that can tune your coupling basically on and off to global laser beams. So this is not a new idea. I want to point out there's been various work done like this, but this is sort of newly the nicest that people have done. So here you can take data, for example, where you say, what is the Rabi rate of a single qubit gate that we drive with lasers? And if we start it here and shift out, you can actually get it to go down to sort of 100th of its strength otherwise. Similarly with fluorescence, if you're trying to do readout, you can basically tune an ion in and out of fluorescence with a readout laser beam. So these have very nice on-off ratios. I want to point out that shifting the ion out doesn't change the qubit frequency. So this is distinct from schemes where people, stark shift atoms or ions out of resonance in order to hide them from laser light. There you have to worry about that stark shift. You have to track that carefully, and you have to know what phase evolution you get. This does not cause shifts on the qubit frequency, and so you don't have that same kind of an issue. And it's sort of an intrinsic thing that you can do very simply just by moving the ion around. No extra laser beams required. You already have the electrodes to trap the ion. So if you want to do entangling gates, right, the way that people typically do entangling gates is we say, all right, we've got our spin, we've got our motion, we're going to do some sort of spin-motion coupling thing, as I described earlier, to make a state-dependent force. And let's use a laser beam to do that, right? Why not? Let's use two, in fact, that are not co-propagating and that are detuned from some upper state. And so people do these gates, and people have demonstrated with this kind of technique Bell state infidelities that you can generate as low as 6 times 10 to the minus 4, which is the current best that I know of in any technology. And there are many different groups that have figured out how to make these errors be sort of a part in 1,000 or a few parts in 1,000 doing gates like this. I also want to point out, AMO folks like lasers. I have AMO imposter syndrome because I didn't do an AMO PhD. And so, so I say, well, gee, how about something that's not lasers, right? There's a problem, though, with these gates, and that is that you need really good lasers. You need stable lasers. You need sort of watt-scale beams, and typically the wavelengths are towards the UV, or at least, you know, in places where you can't just get 100 watts of power from your favorite fiber laser company, like just like that. So this is a challenge for scalability integration. Are you going to put a watt-scale UV laser beam down one of these little tiny integrated waveguides? Probably not, right? I mean, unless you just want to cook it. So, and I will point out that you can put lower power down the waveguides and go to longer wavelengths for some of these things, but it's a real challenge, and there are power dissipation issues too. Secondly, you've got these laser beams, they come in, you're only going to illuminate sort of a few, maybe tens of ions at a time with these laser beams. So either all the ions have to wait their turn for gates, or you need a lot of these lasers and a lot of access, and there's more dissipation. And then finally, you know, this off-resonant scattering thing or phase noise of the laser, those are sort of the dominant gate errors that people typically get with these things. So, you know, why are we going all the way up and all the way down when we could use microwaves? We're sort of right there. We're using microwaves. There's, you know, a microwave signal generation thing is less complicated than a gate laser. You can integrate microwaves and things into a trap, and then, you know, the fact that it's not focused is maybe a bonus. This gives you sort of a global illumination that you can use for lots of things. You can run gates in parallel. So the kicker is you need some kind of a state-dependent force to run an entangling gate, and that requires a gradient of your field. And so basically, your gradient matters over the size scale of the 0-point extent of the ion, which is kind of 10 nanometers. And so basically, if you're using microwaves in free space instead of a laser in free space, you just take a factor of 10 to the 6 hit in your gate Rabi frequency, right? So that's kind of a problem. That's going to be a showstopper. But if you go into the near field of a current carrying wire, much closer than the free space wavelength, you can get a larger gradient. And this is something that Dave Wineland pointed out in a paper 25 years ago now, is that you could actually do some nice spin motion control if you bring this distance down very close to a current carrying wire. And so if you apply sort of amp level currents to a wire in a trap, then you can do entangling operations, state-dependent forces in this way. And there are many groups that have proposed this and done experiments. We've made a trap that does this. It's got current carrying wires in blue here that comes underneath the ions that are trapped up above it. And we operate this cryogenically, and I'll show you some results from this. So the gate scheme that we use, I won't go into detail, but involves driving a strong current at a few megahertz. That's sort of technically easier in various ways. It lets you do the gate in a more power efficient way and with sort of stronger Rabi frequencies than you might otherwise be able to get. There are various ways in which this gate is noise robust that I won't go into. It's a whole talk by itself. There's a few downsides, but you can do a nice gate. So how do you do individual addressing in this context, though, right? You've got two ions. They're right here in this trap. And we can use the fact that we're running these currents through these wires to do the individual addressing as well. So let's say you run a current through this wire up here. The ions are sort of hovering above it. And the qubit frequency gets an AC Zeeman shift. It's the equivalent of an AC Stark shift that you get at a laser beam, but it's a magnetic dipole transition. You get an AC Zeeman shift from it. And so what happens is, because this wire is over here in the near field, the B field drops off. So there's a gradient of the B field, a gradient of the B squared, and thus a gradient of the AC Zeeman shift. And so there's a gradient of the qubit frequency. So if you tip the crystal like this, if you use the electrodes to just shift it a little bit like this, now these two qubits will all of a sudden have different qubit frequencies. And so now you can resolve them in frequency space, and you can drive something that's resonant with this one but not with that one, and do an individually addressed operation. And then when you're done with that, you just turn off the 5 megahertz current. Even if it stays twisted, you know, the qubits go back to being the same frequency. So so this basically, this and this I want to point out is something that works well with our entangling gate that I just described, and so you can do this sort of individual addressing, and there are other schemes for doing laser-free individual addressing as well. that have been performed. So how does this entangling gate, this laser-free gate, come out? And so I'm going to basically show a plot here of Bell state fidelities that you're able to produce. I want to point out Raghu Srinivas was the lead student on this work. So here are different gates based on lasers that have been described in the literature that produce Bell states at the sort of, part in 10 to the 3 error level. There has been other work on laser-free gates as well, where they use microwave frequency gradients instead of these RF gradients. And those, as you can see, they're a bit slower in general, although there's not a hard and fast rule about it, and the fidelity wasn't quite as good. There's a more recent result where if for an additional fidelity hit, you can go another order of magnitude faster and get closer. But what we were able to do is this. And we struggled really hard about this point and this error bar, I will tell you. But this was, we had very great minds like Manny Knill and Scott Glancy and Alex Kwiatkowski, their student who just defended yesterday, thinking very hard about this, and this was the best thing we could come up with. So what I like to say is we're in a statistical tie with the best laser-based gates. So we're here, we're in the mix, right? The other thing I want to point out is all of these were done on 2 qubits in isolation, including ours, and so there's no individual addressing with them. They just made a symmetric Bell state because they had no individual addressability. But we can turn on our individual addressing, and we can actually make a Bell state that's this singlet Bell state, which you can't make just with global control. You have to have individual addressing in order to be able to make a singlet state. And we got a very high fidelity singlet as well. And basically this being off there is down to we didn't exactly tune our individual addressing perfectly. We were wandering around in the dark a little bit as we calibrated these things up. But yes, so basically the take home is that we can do gates that are as good as the best laser-based gates, and they have individual addressing, but they're based on these currents in traps. So now you could think about doing this in parallel, right? So here's a current carrying wire that runs under 3 different electrodes, and you have one set of drive currents that you send down this, and it goes past all the different zones of the trap, and you can do entangling operations simultaneously in all these different zones at once. Right? So even if the gate's a little slower, now you still have this nice simultaneous high fidelity entanglement. It's sufficient to basically change the local trap well confinement in order to address. So now you do that. Now those ones will entangle and this one doesn't. And there's subtleties I can talk about more. If you want to do mixed species entanglement for cooling, for readout, things like that, you just add a few more microwave tones. The gates are very robust to the fact that these wells and these trap areas are not going to be exactly the same. There's a lot of tolerance to Rabi frequency error or motional frequency error, et cetera. And so you can do these nice global gates everywhere. I want to talk briefly about an experiment that's just been done on fully randomized benchmarking. So randomized benchmarking is basically a way to amplify really small errors to extract gate fidelity. So I just showed you this challenge with the error bar. That's because we did one gate and we were trying to understand the fidelity from that. If the error bar is really, really small, then it's very hard to tease out the error rate. But so if you do many gates in a row and you actually randomize the gates in some sequence, so each color is a different kind of a gate, and then at the end you basically say, did those gates prepare the state that I think they should have? You can calculate that. And then you do this many times. Then basically any sort of errors that you have get sort of randomized to an effective sort of decay. And you say, all right, my probability of getting it right decays with the number of gates. And you can extract from this a gate error that's sort of insensitive to how well you do the measurement, how well you do the state preparation, things like that. There's much more subtlety to this, but this is the quick version. But in order to do this, you need to do mini gates. You need to do sort of order 1 over your gate error of gates. And if your gate error is 10 to the minus 3, 4, 5, that turns into a lot of gates. And you need to do mini random sequences for each length. And this is hard for a lot of hardware platforms. And so basically as a hack, they say, all right, we'll make a random sequence, we'll repeat it 100 times. We'll make a different random sequence, we'll repeat it 100 times. And the problem with that is that it doesn't work as well as if you have an exactly fresh sequence every time you run this trial. So basically you get a 4 times smaller uncertainty, what we've seen per wall clock time, so basically 16x in averaging time if you can fully randomize the gates. And it enables a whole bunch of analysis techniques that are very nice. I won't go into it, but basically what we're doing is we're calculating these random gate sequences on the fly so we get a fresh gate sequence each time. And so Alex Kwiatkowski, the theorist on this, and Laz, the postdoc doing the experiment, Laz likes this picture of grommet, basically. We're laying down the gate track as we go, desperately trying to stay ahead of ourselves, but we managed to. So these are the latest results that are in from about a week and a half ago. And so I want to point out here, these are sequences. Laz did 100,000 gates in a row, random sequence, and we're still at 0.8% right answer, right? And basically all randomized benchmarking that's been done before is like down here. And these are several thousand individual trials of this. So there's actually 10 to the 9 basically individual gates that got run in this data set here, all of which was calculated on the fly randomly. And we get a single qubit gate error of 1.6 times 10 to the minus 6, which is basically, again, sort of within statistics and things like that, as good as anybody's ever done. And this error bar, 5 times 10 to the minus 8, that's pretty awesome. And that's the fully randomization that enables you to get that error bar so small. All right, I'll zoom through trap integrated readout. So basically, normally what you do when you're reading out the state of an ion, you hit it with a laser beam, you collect some of the light with an objective, you send it to a camera or a PMT. And if you add more, you just, you need to collect light over a larger area. As distinct from, for example, a tweezer array or an optical lattice, this distance between these sites might be hundreds of microns. And it might be sort of millimeter scale by the time you get out. So we're talking a large field of view that you have to magnify and everything. It becomes tricky to make an objective that's really going to do this well. You can get a lithographic sort of stepper objective if you want, but it's expensive. The other thing too is that then the field of view, if it's smaller than the diameter of your objective, then you'll get blind spots if you want to tile these together. So and then finally, camera readout has challenges in terms of background counts or the speed at which you can get data out that one has to think about. So one alternative would be to integrate photon detectors into the trap itself. So do something like this. So now we're already making the trap. We're already microfabricating everything. Why not put little pixels down here? Instead of collecting light with a lens, just put pixels down there. And lots of people have been thinking about light collection and stuff, but this is sort of, this is first pitch for active little pixels. So the detectors that we use are superconducting nanowire single photon detectors. It's basically a small superconducting nanowire that when you hit it with a photon, it goes normal for a brief period of time, and that sends a voltage pulse out when you bias it with a current. And then it will reset, and then it's ready to count another photon again. And the voltage pulse is very high SNR. You can see this is a nice, easy thing to see with electronics. You can get very high count rates. You can have incredibly low dark counts. You can have sort of good collection area. You can have quantum efficiencies about unity. These are really nice detectors. The questions that we have is basically you're running this detector that likes a microamp bias current next to something that's got tens or hundreds of volts going up and down at tens of megahertz, and it needs to be cryogenic, and how does it treat the ion? I'll point out that others are using other types of detectors. I also want to say that this project was basically a collaboration with Sewu Nam and his group, and really it was fantastic getting to work with Sewu on this, and he very unfortunately died far too young a couple of months ago, but this was really we owe a lot to him for this project having made it to where it is. So anyway, here's a detector trap that I made with Varun Verma, and you can see if you zoom in on this little quantum CCD looking thing here, here is the detector. You send the light over it and for an ion that's there, and you can count the photons with that. You collect about 2% of the photons that come off of the ion. It needs to run at 3.5 Kelvin, which is a bit of an ask, but we made it work. And then here are some, on a log axis, histograms of bright and dark fluorescence counts. And if you look at this, basically these tails here, the sort of incorrect counts, those are due to the atomic physics of beryllium that we're using, not due to the detector. And we were basically able to get a readout error of 9 times 10 to the minus 4 in about 46 microseconds. So it's high fidelity and it's fast, which works nicely. What you'll see, and I won't go into much detail about it, is basically with the RF on, the detector response is different from with it off. And we can model that and we say, OK, it's because of the trap RF inducing currents in this detector. I don't want to go into too much detail. But now Benedict Hampel, an excellent postdoc, has come along and said, all right, now we can put shielding underneath these detectors. We can electrically shield under them, and we should be able to get rid of this. And the upshot is, yes, now we can go to 6 times the voltage. We can operate at 8 Kelvin instead of 3.5 Kelvin because we've chosen a different material. Now this should really work for a wide range of different ion species and not just beryllium. So I'll just close and say, here's this little cartoon that I was talking about. We've talked about we're working on the mixed species. We're working on these detectors. We've got the entangling gates and control here. These are sort of all the pieces. The integrated laser beams is coming, and I'll show you that. But basically, if you tile this together and make your city out of this sort of fully integrated set of technologies, and this is the trap that's coming from MIT Lincoln Labs right now that has all of these features, and we're going to put detectors here, and it's got waveguides there. If you can put all these things together, maybe we can sort of demonstrate a prototype of what might be scalable for trapped ion quantum computing. So with that, I'll thank you for your attention, and I'm happy to take questions. I explained it all.
For this,
I was just curious, so what would you say are like the main Well, it depends. The main source of decoherence is attempting to manipulate the quantum state of the ions. If you just put them in a clock qubit and leave them there, that's the best thing you can do. Unfortunately, that doesn't work for gates. But yeah, so I mean, so it is for decoherence of the encoded quantum information, it's all about the operations that you're doing, and so